Hi, in this video I will explain briefly the different types of intermolecular forces that may exist in organic compounds. The first type of interactions that we are going to discuss are the dipole-dipole interactions or key-sum forces. These forces exist between molecules that have polar bonds and a net dipole moment. So whenever you have a molecule with polar bonds and this molecule has a net dipole moment which is different than zero, so we have a polar molecule, then dipole-dipole interactions will be the main type of interactions that exist between the molecules of these compounds. Polar molecules, as you already know, have regions with low electron density or electron poor regions and regions with high electron density or electron rich regions. And this is because of the difference in electronegativity between the bonded elements. For example, in the case of chloromethane here, the carbon-chlorine bond is a polar bond because chlorine is more electronegative than carbon. So carbon is partially positive or electron poor, and chlorine is partial negative or electron rich. Same thing applies for acetone, where the carbon-oxygen bond is a polar bond, with the carbon being partially positive and oxygen being partially negative. If we look at the electrostatic potential maps of these molecules, we can see that the region around chlorine has a red color, and this means that we have high electron density, and the region around carbon have a blue color, and this is because it is electron poor because of the low electron density. Same thing applies for acetone, where the region around the carbon is blue in color because of the low electron density, and the region around oxygen has a red color because of the high electron density of the molecule. In molecules such as chloromethane or acetone, dipole-dipole interactions will be the main type of interactions that exist between these molecules. Now, the strength of the intermolecular forces or the dipole-dipole interactions are affected by the strengths of the polar bond. So as the net dipole moment or as the polarity of the bond increases, then the strength of the dipole-dipole interactions will increase, and that's why the intermolecular forces that exist between the molecules of these compounds will be higher, will be stronger, and this affects the physical properties such as boiling point and melting point or solubility. For example, in this case, if we compare the melting point and boiling point of isopropyl amine and isopropyl alcohol, we can see that in the case of isopropyl alcohols, the boiling point and the melting point are higher. Why is that? Because the carbon-oxygen bond is more polar than the carbon-nitrogen bond. Since we have a more polar bond, then we have stronger types of interactions, and that's why the intermolecular forces will be stronger, and this affects the physical properties. There is also another factor, which is the hydrogen bonding, which we will be discussing later on. The second type of forces that we will explain are the induced dipole interactions or dipole forces. These mainly exist between non-polar molecules and polar molecules. So if we have a non-polar molecule and a polar molecule, the main type of forces that may exist between these molecules are the induced dipole interactions. For example, if we have a polar molecule and a non-polar molecule, as you can see here, we have high electron density on this side and we have low electron density on this side. The other molecule is non-polar, and that's why we have uniform distribution of electrons. Now what happens is that when this molecule, the polar one, gets in contact with the non-polar one, then because of the high electron density here, electrons which are on the right side of this molecule will be shifted toward the other side because of the repulsion between the electrons. And that's why this molecule will be temporarily polarized. So this molecule now will have high electron density on the left side, which is the side that is away from this molecule, and we have low electron density here, which is the side that is very close to the high electron density region of this molecule. So the molecule on the left side, which was originally non-polar, is now temporarily polar. And that's why we call the interaction induced dipole on this side and dipole on the other side. For example, if we have an acetone molecule, which is a polar molecule, and an isobutane molecule, which is a non-polar one. When acetone gets in contact with this molecule, the high electron density around the oxygen will push the electrons which are here to go to this side, and that's why the isobutane molecule, for example, will be polarized now, and we will have some partial positive here and partial negative charge here. This is again called dipole, induced dipole interaction. The strength of the induced dipole-dipole interaction, of course, depends on the polarity of the polar molecule. So as the polar molecule polarity increases, this will increase the strength of this type of interaction, and also the polarizability of the nonpolar one. By polarizability, we mean the ability of the other molecule to get polarized. So some molecules have high ability, they have certain characteristics or certain properties which makes them highly able to get polarized. Other ones are not. We will discuss this later on. The third type of intermolecular interactions are the induced dipole interactions, or the London dispersion forces. These mainly exist in nonpolar molecules. They exist in polar and nonpolar molecules, but they are only important in nonpolar ones. Why? Because in polar molecules we already have the dipole-dipole interactions, so these are negligible. The London dispersion forces will be negligible. Whereas in nonpolar molecules, the only type of forces that will exist between the molecules are the London dispersion forces, and that's why they gain their importance in this case, case here. For example, if we have two nonpolar molecules, again, they will be both have a uniform distribution of electrons. However, at some point, let's say we have, for some reason, we had some high electron density here in this region here, then this is going to affect the other molecules. So because of the temporarily high electron density in this region of the molecule, the electrons which are in the second molecule will reorganize themselves in a way to minimize repulsion by shifting the electrons to the other side, and that's why this region will be partially positive, this will be partially negative. And again, the induced dipolarity at this molecule here will affect the other molecule, which will also become polar. So at the beginning, both molecules were non-polar, but at some point when they get very close to each other, they will be both temporarily polar. And this mainly causes the appearance of the London dispersion forces. Now these of course are weak forces, and the strengths of these forces basically depend on the surface area of the interacting molecules. As the surface area of the interacting molecules increases, the strength of these forces increases. If we have compounds, or if we are comparing compounds with different number of carbons, then as the number of carbons increases, these forces will be stronger. For example, if we compare the boiling point of butane, pentane, and hexane, we can see that hexane has higher boiling point, which means that we have stronger interactions in the case of hexane. Why? Because hexane has more carbons, it has a large surface area, and a large surface area means higher polarizability, and this means higher London dispersion forces. Now why is that? Whenever you have a larger molecule with a large surface area, then this molecule will have a bigger or larger surface to interact with the other molecule. Whereas if the molecule is smaller, the interaction will be smaller. Same thing applies in here. And that's why as the number of carbons increases, the surface area of the molecule increases, polarizability increases, and the London dispersion forces will be higher. Same thing applies if we are comparing the boiling points of different halogens. As you can see here, iodine has the highest boiling point, whereas fluorine has a lower boiling point compared to the other ones. If we are comparing compounds with different number of carbons with the same number of carbons, and as the number of branches increases, the intermolecular forces will decrease. For example, if we have pentane, which has 5 carbons, isopentane, which has 5 also carbons, and neopentane, which has 5 carbons. Now, the main difference between these two compounds, 3 compounds, is that this one is non-branched, this one has 1 branch, and this one has 2 branches. If you compare the boiling points, you can see that this one has 36 degrees boiling point, 28, and 10. So as the number of branches increases, the boiling point is decreasing. Why is that? Because the surface area of the molecule is decreasing. If you compare the surface area of the first molecule to the second one to the third one, you can see that as branching increases, the molecule will start to get smaller in size. And again, remember that a smaller molecule will have a smaller surface of interaction with other molecules. Whereas if you have a big molecule, the surface of interaction will be higher, and that's why the forces will be higher. And this leads to higher boiling points in case of non-branched alkanes compared to branched ones. These are questions which you can try to solve to check your understanding of the previous lecture.